attempt on seeing if we can learn something about reinforcement learning. So I send you guys some videos. If you watch, there's so many of those videos on YouTube. When I watch them, I think they just talk about its concepts, but just getting into the math and implementing it, I don't see many of those videos very useful. So what I'm gonna do, I'm gonna go actually through the math, a little bit mathematical developments and what it is. It might be a little bit heavy, but we'll see how far we can go. All right. So the idea of reinforcement learning is that you have an agent in this space. Let's say you have a robot. Okay. This could be anything, any autonomous system. And there is an environment, there's a world. Okay. So this is our world. This robot is acting in that space. So the robot, let's say we consider a case that it doesn't know anything about this environment. And you don't have mathematical models to basically figure out the actions for the robot using the first principle math physics that you know, how the system moves in the space. So one thing a robot can do is that the robot can take an action in that space out of all the actions that it can take. So for example, if you have a robot that can go up and down, left and right, the robot can decide, okay, I'm going to take an action, all right? And then see in this world, I take this action, what happens? So in this world, what's going to happen is that you're going to go to a new state. So for example, from here, you're going to go to a new state that is in that world because of the action that you took, and something is going to happen, which we quantify its goodness and badness based on something we define as a reward. So for example, if your objective is to get to a certain point, when you take that action, you look at it and say, okay, am I in that point? You look at it and say, okay, you're not there. The reward for that action, maybe it's -1, okay? So out of the state that you are, there's something called reward, which gauges the goodness or badness of that action that you have taken, all right? If you reach the goal, maybe the reward is gonna be 100, right? So now what you're gonna do, you're gonna take a sequence of actions in the space, and based on the reward that you are collecting from the space, you're gonna gauge your actions, that if this was a good action because it led to a good reward, or if it led to a bad reward, lowered your reward, then you're gonna maybe downgrade taking that action in the future, all right? So this is the whole paradigm of reinforcement learning, that we don't have an understanding about the world, and we explore the space by taking the actions and looking at the reward, all right? So reinforcement learning, it falls into two categories. We have a model base, which I will explain what it is, and then model free. So model-based reinforcement learning is that, for example, I am acting in the environment that I know the entire environment, right? So like you can be in this grid space, and you know where all the obstacles are, right? And you want to find something called a policy, all right? Policy is something that will tell you if you are at this state, for example, if you are at this point, and the goal is to reach this one, all right? What kind of action is a better one? Always, for example, go up, all right? Then the policy at this point always says, if you were there, go up, okay? The policy in that new space is gonna say, go to the right, go to this way and get there, okay? So this is the policy. And the policy is the one that will take you in the least number of the travels, right? Because here, for example, you had this other option to come from downside, right? But you're not going to do this because it's longer. And you know the environment. And in this space, which is called model-based reinforcement learning, we learn about rules and the methods that you can apply still based on this idea of taking an action, collecting a reward, and then just rethinking the rewards that actions that you have taken, you will figure out this shortest paths, okay? So you are going to use the knowledge of the system that you have. Model-free reinforcement learning is the more interesting one, that you are still in the same environment, okay? Like this is obstacles here, all right? But you don't know how the space looks like. You don't even know where the obstacles are. So what happens in model-free reinforcement learning or in model-free learning, there's going to be two type of action. One is called exploration. Okay. Exploration is that you don't think intelligently. So in model-free reinforcement learning, because you know the environment, it's all about how to think intelligently at every location, what kind of a decision I have to make based on the knowledge that I have, all right? But in model-free reinforcement learning, the system goes into the period of exploration. So it starts, it just randomly walks in the environment. It's not just laser focusing on a certain type of actions. And then based on that, it starts acquiring the knowledge about where the obstacles, for example, are. After it acquired some knowledge about the environment, in that knowledge space, then it starts to do exploitation. So the idea of exploitation is that, okay, I learned this much about the environment. Let me take a little bit of a intelligent action. Then after taking a little bit of an intelligent action, I'm going to again start exploring. Then stop, take intelligent actions and keep going between exploration, exploitation. And if you do this many, many times, eventually you're going to have a full knowledge of the environment and the actions that you did optimally based on local information, because you're accumulating the information about the entire space, it's going to be eventually optimal, all right? So this is just the most fascinating part of reinforcement learning. But then to get there, it means that you need to first learn a little bit about model-based optimal decision-making, some foundational knowledge. Then we'll see how far we can go, okay, towards this. You just need to build some foundation. And interesting, the foundational knowledge is very simple. But then it's just that you have to accumulate this and give yourself some time to digest what you are learning. But at the end of the day, I think it's just quite simple. And so today, what I want to go through a succession of examples, and we're going to think about if I know the model of the environment, and I am in a space that we are making decisions at different stages, all right? I am here, I make a decision. My decision impacts what kind of action I'm gonna take in the next stage and so on. So now I want to figure out how should I make the entire decision whole over these stages that I have. So at the end, I get the best result, all right? So let's just start by building some intuition and what we will do. So for this, all right, so let's say we have this problem. So I have this net, right? So I'm at point A to point B. So the goal is to go from point A to point B. And as you are traveling, we have the travel time along every edge, okay? So these are the intersections. So this is like, takes, let's say, 2 hours, this is 1 hour, 5, 10, 5. All right. And then so this is just the road that you have, and the red numbers that you see is this, like how long it takes to travel along every edge. All right. So I want to go from goal is to go from A to B in minimum time. Okay. So you know that if the goal is getting there in minimum time, the total time that it will take is the sum of the time that you spend at every edge, okay? And then in this environment, we know that you can go either up or down, okay? So you cannot go back, all right? So here, let me just take this out. So you can only at every intersection go up or down. So that's the rule. Now I want to find the best path. Okay. So if I want to do that, what would you do as a intelligent decision making? What's your smaller numbers? So one of the policies that feels very natural to human is like greedy. It's called. All right. So how does greedy? This is actually one of the ways that you can always approach a problem. And then when the problems are difficult, this is just the logical heuristics that people use. All right. So what is the idea in the greedy decision making? Is that, okay, I'm going to say I'm at point A. At that point, I have two options, 2 or 1. So I'm going to just choose the best one. So this is going to be, okay, I'm going this way. All right. Now you're arrived at this point, so you have 7 and 9. So you're going to say, okay, I'm going to choose 7 because 7 is better. Then here I'm going to choose 8. I am going to choose 5. I am going to choose, so I have to choose this one. And then here only one choice and that one, okay? So now the total number is 8, 16, 16 plus 5, 21. Right? 21, 27, 37. Okay, so the total is 37. All right. So this is a path that I can obtain, right? And as it turns out, we're going to find it, the optimal value is 36. Okay. So this is not too bad. It's 37. But the thing is that here, this is just for this specific setup. You can clearly see that if the network was a little bit different, as in you choose based on here 2 and 1 and choose 1, then you end up with like a portion of the network that the time is horrendously high, like 70, 90 here. You can see that one greedy decision without knowing what came in front of you, it just put you in a path that you're gonna just score way high travel time than if you had chosen 2. So sequential greedy, or the greedy algorithms, people say it's short-sighted. Okay? So it doesn't always lead to an optimal solution. It just could be put you in a path that eventually it's not a good choice. All right. But many problems that if the average numbers are not as crazy diverse as like having 5, 10, and all of a sudden 70, 90, this is not a bad answer. All right. Now the question is, okay, how can I find the optimal solution? All right. So how can I find optimal solution? One of the ways that you can solve for it is called exhaustive search. Okay. So this is called exhaustive. So exhaustive search, what I would do is I am going to consider create all the possible paths from A to B. I'm going to compute the travel time across all of them. and then pick the one that has the shortest time. All right. So that makes sense. And it is guaranteed always to give you the optimal solution. All right. So let's this space. I'm going to give nodes names A, B. No, B is used. So let's just give different names. So I'm going to just repeat by saying this is C, D, E, F, G, H, I, let's say J, K, L, M, N, O, P. Okay, so let's just try to generate all the possible paths and see how many we'll have. So let me see if I can do it in this space that I can see. Okay, a little bit here. So we are at point A. So one possible path is to go to C. Okay, then the other possible path is go to O. From C, I can have a path that goes to D, all right? And then I can also have a path that goes to from C to F, okay? From O, I can go to F, and from O, I can go to P, okay? So each branch is gonna be one path. From D, I can go to E, okay? Then from F, I can go to G. And from F, I can go to N. From this F, I can go to G. I can go to N. From P, I can go to M. Okay. Then from E, I can go only to H. From G, I can go to H. And I can go to J. From N, I can go to J. And I can go to, from N, I can go to L. From G, I can go to H. And from G also, I can go to J. From N, I can go to J and I can go to L. And from M, I can only go to L. Okay. So from H, I can only go to I. From H, I can only go to I. From J, I can go to I. And I can go to K. From J, I can go to I and K. From L, where's the L? L, I can only go to K. From H, I can only go. From J, I can go to I and K. Again here, I can go to I and K. From L, I can only go to K. And from L, I can only go to K. So you just expand this. From I can go to B. From I can go to B. From I can go to B. From K, I can go to B. I can go to B. From K, I can go to B, to B. So all of them get to B. If I have done it right, I have to have B, and then let's see, it has to be 20 if I have done it right. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think I've missed one node probably in the middle, but you can see just every one of these, like this is gonna be, if I have keep done my job properly. This is one path. This is another one. So just starts here and goes that way and so on, right? So this is going to be all the possible paths. And then you just add up the edge weights and each one scores a number. You exhaustively search the space, you're definitely guaranteed to get optimal solution. All right. Now, what is the challenge? The challenge will be the sheer number of the computations that you have to do if the scale of the problem grows. So let's see. So here are the numbers that you're going to have, interestingly. So if I consider or measure the scale of the problem by what is the size of the grid. So right now this is 3x3 grid, okay? So 4x4 means is that you'll have 4 in this way and 4 in this way. So if you have, if I draw a grid table here, so if your grid is 3x3, the total number of possible paths is 20. So it is manageable. You can just come do the exhaustive search and have all those 20 paths and find the best. Now, if the grid is just extended one more like a cell, it is 4x4, the number of the path goes to 70. So you have to compute 70 paths. If it is 5x5, which is not a big grid event, the total number of possible paths are going to be 252, all right? And then if it is 6, it is going to be 6x6 is 724, right? And then now if you have 7x7, let's add 7x7, then I'll add. If you have 7x7, you have to compute 2,632 paths. So you can see how the numbers are growing. Just slightly extend the space. The number of the paths is just worse than exponential. It's going to be in factorial. It's like, this is the closed form equation that will tell you, so this is divided. So it's this is 2n factorial divided by n factorial squared. So this is the number of the paths that you have to compute. I don't know if you guys worked with factorials. Do you know how do you compute factorials? You can imagine that half the numbers start growing in the factorial sense. So in just a little bit, like if you do 8x8, for example, it's going to be just 10,000 or something, all right? So this growth is not manageable. So what we want is that we are going to study something that would endow us with a process that will reduce these numbers to the number of the paths that you have to compute to 15, 24, 35, 48, 63, okay? Or in a closed form, if I write a formula for it, it's going to be something like this. So what these numbers mean is that an exhaustive search, you needed to create 20 paths to give me the optimal solution. I'm going to introduce something today called dynamic programming. Okay. Which is very related to this reinforcement learning and just some of the, one of the foundational knowledges that we have, which will reduce these numbers that I can give you the optimal solution, guaranteed optimal solution in 3x3 grid by computing 15 paths, in 4x4, 24, but then it shows its impact in the scale. In 7x7, if you do exhaustive search, you have to compute 2,600 paths, but using dynamic programming, if you just do 63 computation, I can tell you what is the optimal path, okay? So this just shows the value, because in robotics, computation takes time, resources, your energy, your battery life, right? So we want to, wherever possible, to avoid exhaustive search. We want smart decision making to cut us the path that we need to take to get the optimal solution, all right? So now let's see if we can digest a little bit of new material that may not come naturally or comfortable first, but we'll see how far we can go. So we are gonna focus on something called This is very important concept in computer science, which is called Bellman's principle of optimality. Okay. So this is just the backbone of all the reinforcement learning. So the whole idea in reinforcement learning is that I don't want to do exhaustive search. I want to have a guided search that would just decrease the number of the actions that I have to take to make an intelligent decision. All right. And it all comes from this Bellman's principle. It is quite intuitive, but let's just see what kind of world we are applying this principle. So we are going to be focusing on the worlds that we have additive reward. So in reinforcement learning, it is mostly focused on a reward. So whatever you get is a reward, and then you always increase your reward. But you can also have a case that you are getting penalized, and you add up your penalties, and you want at the end to have minimum penalty. If it is reward, you're maximizing it. If it is penalty, you want to decrease it. So either way, it's optimal decision making. Okay. So I'm going to describe it based on the maximization, but the example that I prepared, it is based on minimizing the penalty. So it might be not a, just bad exercise case to just get comfortable with this idea of maximum and minimum. Both of them is optimal decision making. So what do we have in terms of the additive reward assumption? So basically, we are living in a world, right, that you are at some state S, okay? And that state, you have multiple choice of actions, okay? So you have action 1, action 2, action 3, okay? And then as a result of taking these actions, you're gonna go to another state, all right? So you have another state, and another state. So you took basically, you're gonna have an S prime, meaning like there's something that says that if you are at state S and take an action AI, meaning for example, A1, A2, A3, then you're gonna end up at another state S prime. I'm putting these indexes. So let's see if you're comfortable, or you can just say this thing, right? As simple as this. I'm at that state, I'm taking an action, and after taking this action, I'm gonna be in another state, okay? And now you're in a space that you end up in this. Now at each one of these, you have other actions to take, okay? And you have other actions to take like this one. Let's say every time you have 3 actions to take. So each one of these actions will take you somewhere, okay? Just like the paths that we had, like we are at a point, like point A, we took 2 actions. We could go at two different places. Like here, my example is 3 action, okay? And then at this point, again, you have 3 more options. This is like all the possible paths, right? And then here you have 3 more options and 3 more options and so on, okay? So this is the space that you are. Now what happens is that you start at some S0, okay? And you take some action A1, something, right? Possible. Then it takes you to state S1, let's say. Then at S1, you take another action, let's call it A2. It takes you to S2. And then at S2, you take action A3, whatever. It doesn't mean like a A1, A2, A3 that I put there. They're dummy variables. I'm just explaining the space that you are, right? So I'm going to go up to, let's say we are at a space that we go as far as 5 steps. A4. A3, S3. Then I take A4 to get to S4. And then I take A5 to get to S5. Okay, so I'm going to go through 5 stages. All right. And at each one of these, if I'm at this state and take this A1, all right, and end up at S1, I am going to get a reward, all right, which is, it could be bad, or if you haven't done good job, you're going to get a negative reward, which means that like you penalized, all right? So what happens is that you have a total reward, which is the reward of, to stay with my notation, let me just change these to the notation I have in my notes. So I take action A0, A1, A2, A3, A4. This is just the notation. So it is going to be reward of S0 and A0 plus the reward of S1 and A1. So these are the rewards that you take for every action. R is S2, A2 plus R S3, A3 plus R S4, A4. Okay, so these are the rewards. And sometimes if you get to the last stage, there might be a final reward there even. Okay, so there's going to be RS5. It's not the action. It's just like you got there, and because of that, you're gonna score something. Okay. So if you get to the goal, you get 100. If you're not, you're gonna get maybe 0 at S5. Okay. So the whole thing is, this is the total reward of the actions that you take, the 5 actions. Now we want to choose for everybody what would be the optimal actions at every stage, what sequence will give us the best one. All right. So for this one, we're going to keep in mind that we are exploring solutions in a world that the total reward, all right, this is going to be the sum of stage rewards. So this is the kind of space that we have, all right? Now, let's get to Bellman's principle in optimality. I'm going to write it. It's going to read a little bit strange, but that is its official definition, but then we're going to try to understand it. So this is the Bellman's principle of optimality. It says that an optimal policy has the property that whatever the initial state and initial decisions are, the remaining decisions must constitute an optimal policy for the state resulting from that decision. So I'm gonna let you guys to read it one more time. Just if you can read my handwriting and see if you can digest it. So to help you guys, let me just write one scenario, right? Let's say I'm in a multi-stage decision-making process, right? So like the one that we had, right? At every intersection, you have 2 choices, all right? And then somebody had come and told me that if you're at state S0, take a 0 star. So this is the optimal actions. It will take you to another state called S1. In there, take you. Okay. All right. So somebody came and said that this is the sequence of actions that you're going to take, right? And because of these actions, you're going to go through these states. And this is the optimal trajectory. So this is the optimal trajectory, meaning that if I just add up the rewards, R1, R0 is the reward of first action, right? R1 star, R2 star, R3 star, and R4 star. This is the best, okay? Best. So somebody has given you this, all right? Now, I'm gonna ask you guys that if I start at S3 and I want to go to S5 or end this process, what is the optimal sequence of action? Okay, so you are now at this S3, okay? At S3. What is the optimal sequence of actions to get to S5? Say it again. So what is here? Can you say louder? Just go to 4 and then 5 using the same actions, right? So S3, S4, S5, right? Taking the same actions that you took before. Okay? So if I ask the same question, start at S1, okay? What are the actions that I can take? So S1, S2, S3, S4. To get to S5, you're going to say that it makes just sense, right? That you have to take the same things. Okay? And then that's going to be the optimal solution. So this is just the principle of optimality. Bellman says that if you have the optimal solution, all right, that you found, this optimal solution has this property that anywhere along the way, if you pick a point in that trajectory and ask, what is the optimal solution to go from that point to the final stage that you are, then the answer is going to be follow through the same path that you generated for S0 at the initial that we started, okay? And the reason is very simple. You can just do it by contradiction. You would say, okay, if there, because the words are all additive, right? If there's another path that you could have taken at S4 or at S1 that is better than the path that you follow through this optimal one that you obtain, then it means that the original one is not optimal, right? There was another option that was shorter. Okay, you would come to to S1, and from there you would have used this shorter one. Okay, so the idea is very, very simple. That if I have the optimal trajectory, everywhere I stop and ask, how should I go? It's just continue. All right. So this is just a principle of optimality. Now, how is this going to be useful to us? Is interesting concept, which brings us to the idea of dynamic programming. So let's see if we can manage this one, okay? So the idea of dynamic programming. If we survive, I have an interesting problem that will maybe make all of this worthwhile. So the whole idea is that let's just see what we have. Imagine this is the point that you want to end up to, okay? And then I have, these are stage states that I have, okay? So from every stage that I have, I can take one action and end up at the final stage, all right? Then this is I'm gonna do it for 3 stages. Then if I am at this stage, at every point, let's say I have 2 options, like the road that we had, all right? So I can go this way and I can go this way, all right? And for each one of these transition, we are getting a reward. So if I go from here to here, the cost or the reward, let's say we do cost, Okay, so we are going to minimize, even though like most of the results are maximizing. But let's say from here to here, there's only one action for me to take, and it will be the cost of 4. Okay, from here to here is only one action, and this is like 1. And then from here to here, it's 5. All right. So from here, I am going to take an this is 2, this is 4. From here, I can go here as in with 3, and let's say I can go here 1, and I can go here with 2. Then from here, I can go here with 1, and I can go here with 5. Then the next stage is here. So I can from here go 3, 4, or I can even go here 5. This one is 1, 2, and 5, and this one is 1 and 5. So we have this network, okay? So what does principle of optimality is gonna do for us? So before that, I have to figure out a way to my iPad. But let's say if we can finish this one here until my laptop can survive. So now what's going to happen, if you use the Bellman's idea, the idea is very simple. If you start from the beginning, right, in our road that you saw, this road that we had, let me draw it again. And then we can execute it on that one. All the weights that we have. So the Bellman's idea is that from the front, you saw like there are 20 options, all right? But if you go backward, there's something that principle of optimality is going to help us with. So let's start here. What is one stage going backward in here? So it gets here, okay? Here, how many options you have? There's only one option, all right? So I can only go this way. And what is the value of that action? It's going to be the value. We're going to introduce something called value function. Okay. The value of this action is 10. Value is going to be, what's the total reward if you start at that point and go to the end, or total penalty that you'll have. So at this point, it's just 10, and I have only one action. Okay. Now I'm going to go one stage back and say, if I were here, at that stage, what is the optimal decision I can make? Okay. So this is going to be just go in that direction, and your value at this point is 11. All right. Now the interesting case happens if I go one more stage back. Okay. So we are going stage backward. So if next stages are here, right? Okay. If I was here, all right, what are the options that is available to me? What I have is 6. If I go this, 6 plus 10, because from that point on, it just takes 10 to go to the final, plus 10, okay? So what I did, this is the reward, this is the reward, 6 of that transition, and then you get to that point, and that point's value going to the optimal point is 10, okay? Plus 10. Then if you are here, there's also another action, okay? So if you take action 1, now if you take action 2, what do you have? You're going to have 7. This is this plus 11, okay? Which is the reward plus the value that you have, okay? So they always follow this pattern, value. So this one ends up being 16. This one ends up being 18, huh? So which one you would choose at that point? We are minimizing. I am going to choose this one, right? And then what is the value of this point? From that point on, you spend 16 to go, okay? 16. Now I can do the same thing with the other nodes. If I am in this stage and I am at that point, what is the option that is available to me for this point? I just have one option, but then I have to go, right? I go down, and here from here on, it's just 10, which is go down, all right? So what is the value of this one? This is 18, okay? Now, in here, it's the same thing. I have just one option. So I would go through 9. I would end up at that point, which from there on, it's 11, okay? So this is going to be 20. All right. Now you can see how I don't need to do exhaustive search, because what's happening is that when I take now to this stage, all right, what are the options in that point for me? I have the option of going 5, which is the reward of that transition or the penalty of that transition. Plus from there on, the optimal path is 18. I don't have to explore different paths that originate from that point on. So this is 18. And from here, you can see if I was doing exhaustive search, I should have considered all these possibilities. Now I'm going to just consider from here on, it is already figured out, optimal. So this is 9 plus 16. So 9 is the transition reward. V is the value of the point that you end up with. So this is going to be what? It is 23. This one is 9, 16. 9 and 16, it's 24, 25, huh? Help me out, 25. So here, then the optimal one is this one. And what is the value of that point is 23, okay? Now, what is the value of this point? There's just one option. 7 plus 18 is gonna be 25, all right? What is the value of this? It's gonna be 5 plus 16 and 12 plus 20. So 5 plus 16 is better, 21. So let's see before my battery runs out. So that is going to be that. And then from here, this is going to be 27. Okay. So now I would go one stage back in here, 10 plus 21, 31, 10, 6 plus 20, this is more. So this is 131. This one is 20, 33, 29. So I'm going to go downward, 29. And then I'm going to go here. From here on, it's 35. From here is 629. So I'm going to go down. Then here, 5 and 25 is 34. 8, this is 34. Okay. And this one is 9 and 31 is 40. 7 and 29 is 30 something. What is it? 36. Now you can see this way it's going to be 37. This way is 36. That's the optimal that we had that 3D didn't choose. Now, after this is done, so you can see how we have a limited number of executions compared to exhaustive search. And what we also have is a valuable thing, because we have something called policy. Policy is a map that any state you choose, it can tell you what is the trajectory to travel to get to the final point in an optimal way, okay? So you choose any point, like somebody might come and say, I want to start here. Give me the optimal trajectory, okay? So what I have, I'm going to look at the policy table and say, okay, go here, go here, go here, go here. And the optimal value is going to be 29, right? So just pick any point that you want. That policy table is going to tell me how to move in that space, all right? So this is something called dynamic programming, what we did. Right. I am rushing because I'm at 3%. I cannot even charge it because I have to take this off, and then let's see. So this is called dynamic programming. Now what I can do is, do you have the charger for your laptop with you? So the idea of the dynamic programming, it's going to be something like this thing, that we have a multi-stage process, right? So we have different stages. So this is a final stage. At final stage, you may end up at different states. And every state has a final value, right? So this is gonna be, let's say the final stage is stage N. So you're gonna have V state 1 at stage N, okay? So it's just a final value. It's a number that you're gonna have. This is the value of state 2 at final stage that you may ended up at. This is S3N and so on. Maybe you have M states, right? At final stage N, okay? So there's a value. Then at every other stage, you have a bunch of states. So this is gonna be not the value. So let me write so you're gonna be having state 1 of stage N minus 1, state 2 of N minus 1, okay? And then maybe in this, you don't have to even have the same thing. So maybe you have N states in that stage, and then you go back the same way. So this is the states that you have. So maybe you have, now this is bunch of, so this is state 1 of stage 1, state 2 of stage 1, and it goes to maybe you have L states at stage 1, and then you have state 1 of stage 0, state 2 of stage 0, and then you go maybe here you have state, say LM, and so you have O states at, not O is not P states at stage 0. So at each stage, you have bunch of actions, right? So you have a bunch of actions that you can take, and they can transfer you to other states, right? So bunch of actions. This is just what is happening. So it's just, you have multiple options. So the dynamic programming basically starts at final stage. And it runs this thing that the value of every state, okay, at every state I, at any stage K, this is equal to, you are maximizing or minimizing. If it's a reward, you are maximizing the reward. If it's a penalty like us that you have to pay for things, you are minimizing. But let me write it with maximum, which is more common. It's gonna be the maximum of the reward of at this stage, right? Taking an action, so the action, all the actions that is available to you, plus the value of the state J, K plus 1, that the future state that you're going to end up at, all right? So you're gonna basically, this means this maximum that you are writing, you're gonna write this expression for every action that you have and where you are ending up, and it has a value, and you're gonna choose the maximum of those as the value of that state, as the value of the state at stage K. And then we're just repeating this from K equal to N minus 1, then you go to N minus 2, and then until you reach to K0, all right? So you're gonna have the values and what action created that value, you're putting it on the network. And at the end of the day, you're gonna have the policy table, all right? So this is the essence of dynamic programming. So I'm gonna stop because I'm almost running out of battery.